Mount Nebo in infrared, an adventure in critical thinking. Footage by JTolanMedia with Taboo conspiracy. Too long didn't read. When presented with evidence of any sort, approach it with curious skepticism. JTolan's incredible infrared footage of Utah mountains is a gold mine, worthy of careful study. Udeuschle Panoramas is a valuable tool, and yes, there will be some math. Let's start with the tallest point in Wales, Udeuschle. A while back, there was an interesting photo that was presented as being a photo of the Alps taken from Wales. I'm showing a cropped version here. Every white dot was named with the name of a prominent mountain, and on first glance, the azimuths checked out. Taboo Conspiracy made a video covering the photo, which included the claim that this was Mont Blanc on the France-Switzerland border, 1,100 kilometers away. At first glance, it appeared compelling, including the distinctive profile of Mont Blanc, a slam dunk for the flat Earth. But let's engage in a bit of skepticism. A recent world record distance photo was shown here with a distance of 443 kilometers. I covered this and other photos in a recent video where I used Udeuschle Panoramas to help visualize things. For comparison, the alleged distance of 1,126 is 2.5 times the distance of the record-setting photo. For an analogy, people have been battling the 4-minute mile for over a century, finally broken by Roger Bannister in 1954. Now, the record stands at 3 minutes and 43 seconds by Hachem El Garouj. Now imagine some fellow claims he's run it in 90 seconds. I would hope some skepticism would be in order. So, what measures could be taken to see if this image is correct? Well, you can drop the location into Peak Finder or Udeuschle Panoramas to get one's bearings and start to make measurements. Personally, I like to find landmarks and then do pixel math so that we could turn the photo into a source of calibration. Using various tools, we can find azimuth values and the X location in pixels for our two landmark mountains, and then subtract to find the delta, giving us a ratio which we can then apply to other areas of the photo. This is not scientific, but it will give us an apples-to-apples comparison, such as discovering that quote-unquote Mont Blanc is 19 pixels wide, resulting in a lateral angular size of 0.688 degrees, which we'll use on the next screen. So we know the latitude and longitude of Udeuschle and Mont Blanc, so we can drop them into an azimuth and distance calculator, giving us a distance of 1,126 kilometers, and helping us confirm that the thing labeled Mont Blanc is indeed at the right azimuth, more or less. But we're more interested in how big the prominence of Mont Blanc is at that distance, so we'll use the angular size calculator from 1728.com. We enter the angular size of 0.688 degrees from the previous slide, and the distance of 1125.7 kilometers, resulting in a prominence width of 13.5 kilometers. How does this compare to the real mountain? We need to get a view of Mont Blanc from the direction of Udeuschle. If we start with Google Maps, their view of Mont Blanc, we can draw an arrow back to Udeuschle. If we click on the little Street View man, we can not only see roads highlighted in blue where the Street View camera car has driven, but also little blue circles showing where people have taken 360-degree scenic photos called photospheres. Let's go to this one, where Fabian Gregus snapped this image of the real Mont Blanc. And let's start with a Peak Finder image of the prominence of Mont Blanc and two nearby peaks, forming a crown shape with Mont Blanc. If we plot them on a map, then we can use a distance measuring tool to learn that they're less than 6 kilometers apart. This is not exactly at right angles to our line of sight with Udeuschle, but it's close enough to see that the Mont Blanc prominence profile is twice as small as what it's claimed to be in the original photo. Here is the real Mont Blanc actual size compared to the cloud. You might say, that's too much math. There's another area of exploration, and that's the image that Ben used to sell the Mont Blanc profile in the original photo. After a little digging, I found an almost identical photo shot from a now closed resort named Le Chalet Bouvard, shown here on the map, compared to Mont Blanc. Clearly not the same flank of the mountain as it would be seen from Ur-Witwa. It was a nice photo, shown cropped here, but those are not the Alps. Those are just clouds. So this brings us to the purpose of this video, analyzing some of the images that JTolanMedia has shared of a recent flight that he took across southern Utah with an amazing infrared zoom camera. I watched his video with fascination, but did nothing with it because I didn't have any specifics. Last week, Taboo Conspiracy Ben did the detective work and tracked down where JTolan shot his footage, and it matched perfectly. I used Ben's work as my starting place for my own analysis. One of the phrases that JTolan makes repeatedly throughout his video is how flat the Earth looks. And Ben picks up on this theme, saying his footage proves flat Earth. But does it? We can all agree that the Earth appears flat. Is this possible even if the Earth were a globe? Let's do an analysis of what one can see through an airplane window with an approximate view of 45 degrees and a distance to the horizon of 369 kilometers. Doing a little math with the area of a circle, specifically 1/8 for a 45 degree, gives us a 53,000 square kilometers. Now let's compare this to the planet Earth, this time with surface area. We find that an airplane passenger can see 0.03% of the total surface of Earth. Now let's try this another way, using JTolan's footage, using Udeuschle to visualize it. Clicking on the four corners gives us those actual map locations, which can be pinned in Google Earth and turned into a polygon, which shows an area of about 33,000 square kilometers, less than the theoretical value from above because his flight was only at 8,500 meters. Which means that in JTolan's footage, we're seeing about 0.02% of Earth's surface. The Earth could look flat because it is flat, or it could look flat because the Earth is so big. Let's compare this to a basketball. A standard basketball has thousands of pebbles for texture and grip, so let's just focus in on the size of the pebble, not its shape. Doing the math, we see that the area we can see from 8,500 meters in an airplane is a fraction of a single pebble. In this animation, the airplane is shown about 1,000 times larger than it would be to scale. I did the math, and an actual airplane is less than the size of a single pixel. This is a huge concept. Many flat Earth folks look around themselves, even from a high vantage point, such as an airplane, and are completely overwhelmed by a lack of visible curvature. If it's a globe with radius 6,371 kilometers, it will appear just as flat as if it were really flat. So what's needed are precision observations. A quick aside here. There are two kinds of observations, casual and precise. Casual observations shouldn't be discounted so long as they're placed into perspective. If you really want to figure out relationships, precise calibrated observations are where it's at. That's one of the phrases I repeat over and over throughout the do-it-yourself explorations all over my channel. Interestingly, some folks are allergic to precise observations because they know it will give the game away. Remember Saragaki, author of Saragaki's Jabberwocky? Here he is responding to my suggestion that folks go outside and make careful observations. To his credit, he's the only fellow I know to have written a proof using the axioms of imaginometry. Just imagine proving that a horizontal line is parallel to a vertical one. Getting back to Ben's video, I left a comment for him, and I mentioned Mount Nebo and Mount Timpanogos, and how Mount Nebo appears taller in JTolan's footage, even though Mount Timpanogos should. It's an interesting geometry puzzle because it's not obvious what the answer should be. Mount Timpanogos is definitely shorter than Mount Nebo, but in real life, it's further away. And an analogy is this photo of two women. Can you tell who is actually taller? The brunette is clearly shorter, and further away, but she appears higher in our field of view because of our vantage point. So let's figure out an easy method requiring no trigonometry. We'll draw both mountains on the same baseline with our elevated observer, and this is assuming flat Earth. And let's imagine our sightline to Mount Timpanogos with a pink right triangle and to Mount Nebo with a green one. The difference is subtle, but we can see in this example that Mount Nebo should appear slightly higher. So let's try to elevate our observer and see the difference. Here, clearly Mount Timpanogos will appear higher in the frame. So how can we quantify this? We can look at the slope of the hypotenuse. A less steep slope, a gentler slope, will appear higher, while a steeper slope will appear lower. Now we just need to define the right triangle. The base of the right triangle will be the distance to the mountain, and the height of the right triangle will be the elevation of the airplane minus the height of the mountain. So here's our question. From an observer with elevation 8534 meters, which should appear higher in the frame, Mount Nebo or Mount Timpanogos? As we've mentioned, the answer is not obvious, since it's possible the shorter and more distant Mount Timpanogos will appear higher, just like the brunette in the photo, because of the elevation of the observer. Let's illustrate this scenario with for a flat Earth just using slope, rise over run. We'll make a right triangle being the height above the Mount Timpanogos summit, and we'll repeat the process with Mount Nebo, and the steeper downward slope will indicate lower in the frame. In this case, Mount Nebo should appear lower in the frame if the Earth were flat. And now let's repeat the procedure with a globe Earth, but to handicap the globers, we won't take refraction into account. Using Metabunk's Earth Curve calculator and using the geometric results section, which ignores refraction, we'll also set the viewer height to 0, giving us a pure drop value in this case. 10,070 meters for the Mount Timpanogos at 358 kilometers distance. So things get a little interesting for our right triangles with the globe, but the geometric drop values make things really easy. So let's draw an imaginary horizontal line from which the airplane's altitude is calculated. And like before, we'll draw a pink triangle and a green triangle for the two mountains, with acute angles at each peak. On the previous screen, we calculated that the geometric drop for Mount Timpanogos, as measured from an observer with 0 height, but this is more than the mountain's height of 3580. So when we add the negative drop value to the positive height, we still end up with a negative 6490. This is the effective height of Mount Timpanogos measured against a 0 baseline. We're now ready to measure the triangle with a baseline of 358 kilometers, aka the distance to the mountain, and a height of 15,024 meters. We took the airplane's height and subtracted the negative height of the mountain. Well, when you subtract the negative, you actually add, resulting in a much higher elevation due to the curvature of the Earth. But the result is quite subtle. With a gentler slope to the target, Mount Nebo will appear higher in the frame than Mount Timpanogos. So let's review. To keep things consistent with right triangles, we'll simply compute the geometric drop using the Metabunk calculator, ignoring refraction, and then subtract that from the height of the mountain. And when we subtract the final mountain's height from the elevation of the airplane, we must really add, because we're subtracting a negative. We'll repeat with Mount Nebo, and then again, the steeper slope will indicate that the mountain will appear lower in the frame. So in this case, we are predicting that if the Earth were a globe, Mount Nebo should appear taller than Mount Timpanogos. So let's summarize our analysis that we did with simple geometry. You can obviously do a more sophisticated one using trigonometry, but all we were doing is predicting higher versus lower. If the Earth were flat, Mount Timpanogos should appear higher, while if the Earth were a globe, neglecting refraction, Mount Nebo should appear higher in frame. So let's grab a frame from JTolan's footage via Ben's video and see if we can duplicate it in Udeuschle Panoramas. There were so many interesting images, but Mount Nebo was the star of the show. So I grabbed this frame showing the peaks of Mount Timpanogos to the right. I started with observation point latitude longitude given by Ben, but I quickly discovered that parallax is a bear. While the location matched the initial wide-angle shot, the plane was doing 432 knots as he zoomed in on various features. So this took a bit of trial and error, and I'm still not exact, but here's what I came up with. Let's take a look at the two most important settings, the observer height, which I just copied from the flight tracker data, and latitude longitude, which is several seconds later in the flight path from Ben's observation point, which was at the start of the zoom. So the aircraft have traveled a little bit before the image that I selected. After the initial plot, I used the 10x telescope in Udeuschle. So here's the image. In addition to Mount Nebo and the several peaks of Mount Timpanogos, we have a few notable features that I had fun exploring. This Zorro Z slash is actually a canyon called Cyclone Draw. It no longer looks like a Z, but it turns out that we're looking at the canyon, the line of the canyon, from such a low angle that it compresses a long canyon into a sharp zigzag. Another feature which really helped with the parallax is Dr. Canyon, which feeds into Fish Lake, which is hidden behind the terrain in the original image. All in all, I was very pleased with how it came out using Udeuschle's standard settings. So, thanks to Ole D, I've learned that there is a refraction setting in Udeuschle that can help us see a flat Earth version, where a horizontal vantage point is synonymous with level, equal elevations. Simply type underscore RC1 at the end of the range parameter. Basically, when you set RC1, your eye level will be parallel to level, or equal elevations. Let's test this out with two mountains that I picked out of a list of mountain peaks in Utah. Mount Nebo and Bald Mountain are very close in height, but it turns out the height data in Udeuschle is slightly different, but close enough for this experiment. The plan is to create a sight line from Mount Nebo to Bald Mountain, with the camera set to the height of Mount Nebo, and the refraction coefficient set to 1, or flat Earth. We should expect the peaks of the two mountains to both be at eye level. I picked an observation point southwest of the town of Nephi so that Mount Nebo will appear to the left of Bald Mountain in our view. Here are the settings in Udeuschle, and we're setting the refraction coefficient to 1 for flat Earth, but to reduce screen clutter, we're capping the range at 150 kilometers and color coding to match. And here's the result. Even though Bald Mountain is over 140 kilometers away, it will appear the same level as Mount Nebo for an observer at that eye level. So level truly is horizontal, when the refraction coefficient is set to 1, as with a flat Earth. But RC1 is not the only possible setting. You can go all the way down to 0 to simulate a globe with no refraction. Wouldn't it be cool to take our original Udeuschle image with factory default settings and take it through a range of refraction coefficient settings? This will only take me several hours to screen cap everything and align it just right, but it should be fun. Now, before we show the original image sequence, we need to prepare ourselves so we can make sense of what we're about to see. So let's start with an orthographic side view where the curvature is hugely exaggerated here, and see what happens when we flatten the baseline. So watch what happens at the top of the screen when we go from RC0 to RC1 for a flat Earth. Now we'll repeat it again so you can watch what happens on the screen. Here we're back at RC0 for a globe Earth with no refraction. And now watch the screen as we transition to RC1 for a flat Earth. Notice that since we've anchored the red object in our field of view, the objects in the back appear to rise up. Now the effect is so striking that you're going to be convinced that I'm changing observer height. I am not. But just for fun, here's a visualization of what our brain thinks is happening. we might imagine the observer getting higher, and that's why we can see the green object behind the red one. But this is, this is not the case. Let's do it again, but this time you can watch the screen. And this is not what's really happening. Did I mention that I'm not changing the observer height when I present the series of 12 Udeuschle images? So here's what's really happening as we go from RC0 to RC1. All right, the stuff in the back is going to appear to rise up, but we're just changing the refraction coefficient as we go from a globe to a simulated flat Earth. So before I show you the 12 image sequence, I'd like to again share my Udeuschle settings, which you're welcome to duplicate for yourself. To have the RC image sequence make sense compared to this infrared image, let's mark it up with some lines, which I'll leave on screen as we scroll through the RC values from 0 to 1. So first we have Mount Nebo, and then the Mount Timpanogos peaks. Next is the Cyclone Draw Canyon, and the Doctor Canyon, feeding into the hidden Fish Lake. North of Fish Lake, there's a hill containing Doctor Canyon with a high point called Fish Lake Hightop. Next is Loafer Mountain and Santaquin Peaks, which are really two peaks on the same mountain. And speaking of the same mountain, Bomber Peak is actually one of the peaks on Mount Timpanogos, named for the location where a B-25 crashed in bad weather in 1955. The Pfeifferhorn and White Baldy are also two peaks on the same mountain, just north of Box Elder Peak. And Salt Creek Peak is actually in front of Mount Nebo, southeast to the town of Nephi, named after a personal hero of mine. Still further in front of Mount Nebo, closer to the observer, is Levin Peak. Now, when I show the actual image sequence, I decided to anchor each image with the peak of Mount Nebo staying in the same place in the frame. Because I was doing the telescope feature by hand, you'll notice in some of the arrows to the mountain peaks will move a little bit. But you should see the peak of Mount Nebo staying in the same place throughout. So let's play the animation going through the 12 images from RC0 through RC1. And here we are at RC 1.0 for the flat Earth. So let's go back down to RC0 a little bit faster this time. So I think now would be a good time to remind you that I am not changing observer height. It's crazy, isn't it? But let's play the animation again and see if you can use the markings to figure out which of the 12 images is closest to JTolan's original footage. So again, we'll do this a little bit more quickly this time. So let's just take a look at it to see how far some of those features have moved. So this is where they are. This is where they were in the original image, the original infrared image, and here's where they are in this current image on screen. So let's go back down to RC0. In fact, actually, we'll not quite get there. Try to figure out which image is best is the challenge. Now you'll notice that I stopped at 0.15 for a reason. I think it's just a hair better than 0.2. So let's compare it to the original. Without the reference marks. We'll do a blink test for 0.15. So here's the original image, just going back and forth. Now let's do a blink test with 0.2. All right, I think it's pretty close. If I thought about this sooner, I could have done 0.175. Now let's revisit the prediction of what should appear higher in the frame, Mount Nebo or Mount Timpanogos. Now our analysis was done purely with geometry and math before we did any of the Udeuschle visualizations. But the flat Earth prediction was that Mount Timpanogos would appear higher, as confirmed here. And that on a globe Earth, Mount Nebo would appear higher in the frame, confirmed here with the RC 0.15 setting. And here's the original again. So let's finish with a central claim of Ben's video, that Utah Lake should be hidden by curvature if we lived on a globe. And he's right. So I have a question. Is that really Utah Lake? So let's start with a little geography. North by northwest of Mount Nebo are two mountains, West Mountain and the Lake Mountains, with Utah Lake between them. And here's the view using RC1 flat Earth setting, where the lake is indeed visible between those two mountains. So it seems like Ben might be onto something. But one thing that Ben mentioned why he knew it was Utah Lake was its color. You know what else has that color? The sky. Almost the entire sky. So, is that really Utah Lake? Let me use 5 of my friends here to help answer this question. Masking. I say what's labeled Utah Lake is really just sky. Now, what if we mask out the land, leaving Utah Lake untouched? Can we tell the difference? So here comes the mask, and it really is hard to tell between Utah Lake and the sky. Are there other examples of water in JTolan's infrared footage? Why, yes, there are several, including the Wide Hollow Reservoir near the town of Escalante, looking as black as midnight. Please notice the flat top mountain and Mount Nebo at the top of this image, specifically the color of what's between them. We're going to cover that in a few moments. But JTolan has taken other flights and captured infrared also, such as this flight from Los Angeles. So here's a Google Earth or Google Maps image, and here's the infrared. A black Pacific Ocean. Here's more Pacific Ocean later in that flight, looking like India ink. And this shot looks like a lake, but is actually the Pacific with just a lot of cloud cover. The skyscrapers of Los Angeles look like stubble, and the water looks black as midnight. Now, speaking of water, what if we let JTolan's video play past where Ben freeze-framed it? So he paused the video here and then spent quite a bit of time talking about Utah Lake. But I wanted to get it straight from the horse's mouth, so I went to the original source video and found the exact frame. 8 minutes, 13 seconds, 13 frames. Now what happens if we press play? 5 seconds later, we see a vivid example of water in infrared with the Otter Creek Reservoir. Blacker than black. So let's do a little split screen and see what was on screen just 5 seconds earlier. Utah Lake doesn't look very much like water when we put them next to each other. Now, next we have azimuths, or more specifically, line of sight. JTolan's original video has a clip taken from earlier in the flight where he pans from Mount Nebo to the left to capture Flat Top Mountain, showing this pair of screen captures as he panned. Notice the Dr. Canyon's position, showing that it is several seconds earlier in the flight from our initial Udeuschle analysis. With a bit of detective work, I was able to locate the position of the plane, which I'm calling location 2. So why is this important? Well, it gives us another view of the region to the left of Mount Nebo, where Utah Lake is supposed to be. So let's compare the colors of this region. It looks gray, gray, gray to me. In the upper image, the entire valley between Mount Nebo and Flat Top is the same exact color, even darker than what Ben called Utah Lake. Now let's bring in the azimuths between Mount Nebo and Flat Top. If we start to the left of West Mountain and pan to the left, you see that less than half of that region is Utah Lake. Yet, in the original footage, the entire valley is that same uniform color. So let's bring out the sharpest knife in the drawer, Udeuschle, and we'll keep it at the default setting, which is RC 0.15. Let's start with the valley between Mount Nebo and Flat Top and bring in the visualization. It looks like a perfect fit. What's above this is sky, just sky. Let's try it again with Ben's freeze frame. Is that Utah Lake? Let's see if it fits. Another perfect match. I'd say that is not Utah Lake, but rather sky, sky, sky. Just for fun, let's see how things would look like on a flat Earth. here's the original infrared, and here's what Udeuschle visualized with the globe model with standard refraction, and here's the flat Earth version. And you could see for yourself which one matches reality. Critical thinking. People are always looking for proof for their side of the argument. I would simply urge caution if that proof is fuzzy, blurry, or otherwise indistinct. Is that Crete from Israel? Is that Mont Blanc from Wales? Is that Utah Lake? I recommend everyone take new evidence that crosses your threshold and examine it skeptically. Can you pick it apart, dissect it, rather than accept it blindly if it supports your side? I don't care if that guy holds up a Rorschach inkblot and calls it globe proof. The key here is critical thinking. Think like a critic. Pick holes in the argument. Find the flaws. Don't just repeat what your side says. Some classic examples of lacking critical thinking are two phenomena which supposedly show a local sun, which is canonical to a flat Earth model. People say crepuscular rays prove the sun is local. Then what exactly does this image mean? What does it really mean, using this reasoning, taken to its logical end? It means the sun is literally behind that tall tree, by a matter of feet. But we know that half of the entire surface of Earth can see the sun at the same time. Next, is there a sun in front of the clouds? Let's pick this apart. Visible clouds for any observer are at most a few hundred kilometers away, and only a few kilometers high in altitude at most of the time. But the tallest clouds on record have only gone 85 kilometers up, and that's extremely rare. If the sun is truly in front of the clouds, it means the sun must be at a lower altitude than 85 kilometers. But again, being that half of Earth must be able to experience daylight, exactly how is this sun supposed to accomplish that? We also get very funny images such as this one, showing the sun to be in front of the crane, but behind the rocket, even though they're right next to each other. Most recently, I was sent a link to a fascinating video entitled Moon Below the Horizon by an enthusiastic flat earther named Lair Bear. Let's pull on this thread and just take it at face value. Let's just say the moon truly is below the horizon. So let's say the plane is at 10,000 meters in altitude, and let's compare it to this photo of the plane flying over ocean. So this means that if the moon is below the horizon, it must be very low, practically sitting on the ocean surface. And again, what about the rest of the Earth? When the moon is not a new moon, fully half of the entire surface of Earth will see it in the sky, weather permitting. Exactly how is this possible if the moon is bobbing on the surface of the ocean? Or, taking a look at the original photo, the original footage, is it possible that due to haze, we cannot see the horizon, and we're just seeing the belt of Venus, which would coincide with the full moon? So, the next time someone gives you a very attractive photo or video, don't take her word for it, because you might be getting catfished. Proof is very hard to come by, so please be careful with throwing that word around casually. Call it evidence, and try to cross-examine it as best you can. You'll be the better for it. If you really want to do some critical thinking, along with putting your geometry skills to the test, may I remind you of my Dirty Dozen Eclipse Predictions Challenge. Here's all you need to complete the challenge. I recommend plenty of paper for your sketches and a spreadsheet to hold your calculations. Many folks have already plowed through most of the items, and I'll soon publish the official answer key, so we can all compare our results to each other and see who can get the closest mathematically. So, special thanks to my channel supporters, Johnny Ragadoo and Luke Filewalker, and rest in peace, Jim Jackson. As always, please be kind to each other in the comments. If someone insults you, it says more about him or her than you, so there's no need to respond in kind. Laugh it off to show that your feathers can't get easily ruffled. And as they say, don't feed the trolls. Bye.